So as Rob mentioned, I'm Heather Adkins, Director of Information Security and Privacy at Google. And I help, along with a fairly sizable team, run the detection and response organization. In other words, we find bad guys and we make them cry. And that's the thing that we love to do day to day. A little bit about me before we get started so that you understand the method to my madness. I grew up in a small little town in the desert where there wasn't much to do but learn computers and read, and that's what I did. I fell in love with technology at a very early age. But when I went to college, I decided I wanted to be somewhere where it rained and where there was green stuff. So I studied marine biology up in the northern coast of California. And there I fell in love with the idea of ecosystems and understanding how organisms work inside of them. And then at some point in my career, and I still don't understand why I did this, I started studying medieval history. And if you know anything about the study of medieval history, you know it is the sort of identification of really arcane artifacts and building stories. And it turns out that when you combine all three of my great loves, technology, ecosystems, arcane artifacts, it looks a little bit like digital forensics. Okay. And that's actually what I more or less love doing even today. And I've been at Google long enough, 15 years now, to see us do everything from launching Gmail to putting balloons into almost outer space to provide Wi-Fi for the whole world. And so I've gotten to see a whole lot of things. But it also means that in my old age, I've become somewhat whimsical and philosophical. So we are going to start in a somewhat unusual place with this question: why are we here? There's a literal answer to this. All of you are here because you're interested in threat hunting. Perhaps you've been doing it for a little while and you love the community. Or perhaps you're new and you don't know what it is. Or perhaps you heard that threat hunting was something you needed to have and you're here to get you one. Okay. And you're hoping Rob is going to hand it to you on the way out. That is the literal reason why you are here. But that is not really the reason you are here. You are here in your field, in this specialty, and in your career because of events that have unfolded over the last 45 years. Beginning in the 1960s, the US government realized they had a problem on their hand. Systems were no longer single user. We suddenly had multiple users, and we had resource sharing. And they realized pretty early on that they had a problem, and that if two users were using the system at the same time, they might be able to see each other's stuff. And they studied this pretty deeply. And by 1972, James Anderson had written what I believe is the seminal topic, or the seminal paper on this topic. He posited quite correctly that the things we were building could not defend themselves. And he realized this in 1972. This is an incredible paper. If you haven't read it, there's a source here on the bottom of the slides. He was a meteorologist. He understood how systems worked. He understood the push and the pull, and he could see the future as things became connected. This is a great paper. He talks about the fact that CPU registers aren't private from one another. He predicted the buffer overflow. We knew everything we needed to know in 1972. And the government did start to work on this. And by 1980, he had further posited that we needed to start auditing what users did on their systems. He wrote a paper about it called Computer Security Threat Monitoring and Surveillance. It's also a seminal paper in our field. It is the paper that started the careers that all of you have today. And again, he predicted everything we were going to do. He knew that we needed auditing records. He knew that we needed people looking at them. He knew we needed to centralize them. He knew that log loss would be a problem. And mind you, he's working on systems that are just barely multi-user. We just barely have Unix at this point. There is no Mac. There is no Windows. Okay. And they start talking about the kinds of auditing that need to be done. Each box here sort of roughly represents a topic that turns up in the academic literature or in products that are being commercially made. And the very first technique that they suggest we try is manual analysis, just literally humans finding stuff in logs. Very shortly after that, Dorothy Denning out of SRI starts talking about behavioral anomalies. early. What does normal look like? How do we determine what abnormal is? Can we use statistics for that? Can we use self-learning? Can we use expert systems? All of this comes very early in the 80s. And by the 90s, we've moved on to what we think of today as the big stuff, right? Neural networks, genetic algorithms, AI, data mining. We give people analysis GUIs so that they can click through things very easily to sort and find. Does this sound familiar? Have we been talking about this for the last 2 days? Conceptually, our ancestors thought of this already. And then by the 2000s, we sort of start to combine it all, really talk deeply about machine learning. And it's very interesting to see how all of this progressed. And there's one thing that all of these technologies have in common. All of these technologies were meant to be assistants. They were meant to point a human in a direction. And I call this the Elmer Fudd theory, right? So we are humans, we are out there hunting, we are looking for things. And that has always been conceptually what we had in mind. Machine learning, these kinds of concepts were really meant to assist the human. And indeed, for any of you who have ever started a SOC, your SOC probably starts out looking a little bit like this. This is actually something we made when we started the Google SOC. We literally just hired analysts to stare at logs until we knew what to do with them. Right? And that is actually what the original intent was behind our careers. So it's not surprising that when we read that literature, just look at this timeline in a different way, when we look at the literature, we've been classified, we've been given names. James Anderson called this the activity security officer, which sounds pretty cool. I want to be an officer, right? Get a badge, I'm a little bit like a cop. And interestingly enough, a lot of the people who went into this field at this time are computer operators, many of them women. Not so many women in this room today, which I think is an interesting observation for another talk. We start to see words like auditor, right? Security analyst is born in the 80s. I found a job with a company that shall not be named, hiring security analysts, right? So this job has been around for a long time. Fast forward, and we start to see security administrator, which is a twist on IT administrator. And in the 2000s, late 1990s, we invent the SOC, a collection of these folks to do this work. And then for some reason, we invented the term threat hunter. But the work is relatively the same. Assisted by technology, humans find bad stuff. And that is, relatively speaking, what threat hunting is today. And why do we keep sort of reinventing this? I have a bit of a hypothesis. It's a poorly constructed one, probably won't hold a lot of weight, but I have this kind of feeling that over the years, about every 4 to 5 years, something's not working right. We're not detecting what we think we should be. And so we start anew. And we start with humans. We always start with analysts. But analysts need data. And once you give them data, they've got too much. And so naturally, we build them tools. We build them assistants. But then it turns out that that doesn't work either. And we know that humans can do it better. And we start up in the same place. But when we look at this over time, we look at the kinds of technology that have been available, the intelligent assistants that we've been giving people. It begins with something very simple. Have you read Cliff Stoll's book on the cuckoo's egg? If you haven't, this is part of your homework between now and when you get home. He had literally nothing. And what he did to chase the hacker in a story, and I won't spoil the story for you, he set up a trigger. And every time the hacker logged in, he printed the audit records out. And I don't mean to the screen. I mean to a printer. And not a laser printer that goes fast, but a line printer that printed out very slowly everything that the attacker did and everything the attacker saw. This is also James Anderson's original advice. Print out the audit records, create a case file, hand it to an officer to read and to review. But you can imagine that the people doing this work don't find that very rewarding, and it doesn't work. And so we invent new technology for them. We invented database-backed GUIs with a SQL interface that went to a pager when rules were fired. We invented that in the 80s. We got a little more sophisticated by the time we got to the 2000s, where we were doing signatures in the SIEM, and we put a SOC in place to look at it 24/7. And now we have threat hunting tools. We also have SIEMs. We have data science, and gosh, goodness knows what else. Right? Every 5 years or so, we go through this revolution of trying to improve the intelligent assistance. There's a recent study out from RAND, and this is going to sound a little bit strange, but there's a recent study out from RAND on the estimated length of career for exploit developers. And these are people who routinely and repeatedly do it and are successful at it. And they posit that the average career time doing that kind of work is about 4 years. There are a few reasons for that. One, they use up their skill set entirely during that 4-year time, and they find all the low-hanging fruit, and the next one is that much harder. It's also very intensive work. I think looking at cognitive science in this field is really important because the work is really intense if you're doing it all the time. And that's another reason why people fall out of it. And I think the same is probably true for our threat hunters. At Google, I think, I don't know anyone who's been in my team who hasn't asked for a job change after 4 years. They love Google, they love the kind of work we do, they want to stay in the team, but they want to do threat intelligence. They want to do forensics. They don't want to just find bad guys. The work gets repetitive, it gets boring, the assistants are not helpful enough. And this is a problem. If you're a manager and you're building your SOC, you got to know that your people aren't going to stay for very long. 4 years is probably the amount of time that you have. That's pretty depressing, and I'm sorry. But let's look at the future, because I think that the future really holds something quite valuable, and I'm going to be somewhat controversial with this. I think ultimately, by 2050 or so, we will have put in place something to solve James Anderson's original problem. We will have systems that can defend themselves. They'll either be better constructed and/or they'll be self-healing. Which means that the system we have today, where the machines are reliant on the humans to defend them, will be less and less relevant. And that's ultimately the solution, the fix, if you will, to the security problem. But it's going to take a little while to get there. I'm actually quite hopeful that we will make it. In 2016, August 2016, at Black Hat DEF CON, Team Mayhem won the DARPA Cyber Grand Challenge. And this challenge put these teams over a period of 2 years was to build a cyber reasoning system that could detect vulnerabilities and patch them. In other words, a system that could heal itself. And they did have a winner. Unfortunately, it didn't do very well when it played against the humans in CTF. But it was also installed in the Smithsonian this week, which is quite exciting. But I think this is the future, and we will figure it out at some point. And the question is, what's the role of the human in this life cycle? The real reason you are here, the real meaning behind your work, is that once we've built a system that can learn, we are going to have to teach it everything we know. All of the work that you do to understand how threats work, how to defend systems, what attacks look like, how attackers work, how governments build teams to attack other systems, all of that will play into how we teach the computers to defend themselves. And that's the real reason why we are here. And in the meantime, we get to defend and chase bad guys too. And I will point out that this Terminator magical future will be able to spell for itself. Better than me. My CEO is very fond of saying this kind of thing, that we will have intelligent assistants that will be able to help us as we move forward. Turns out you've actually been building them all along, right? They will start to get more and more intelligent. Right now, ours, if you say, "Okay, Google, what is Burger King?" may not read out what you expect it to. But it will become more intelligent and they will be more helpful. Imagine being able to say, "Okay, Splunk, am I compromised by APT 28? And then while you're in there, look for APT 29 too, and it replying back, "No, you're not compromised, and I've downloaded all the threat intelligence. I've incorporated it into the defense, and I'll let you know if I see anything." We probably won't speak to it, but you can get the kind of the idea of what these intelligent assistants will do in the future. Let's talk a little bit about Google. I'll spend the rest of the time talking about threat hunting in Google. Our detection pipeline probably doesn't look that remarkable relative to what you're used to. We ingest hundreds and hundreds of gigabytes every day, and we store it for long periods of time in a large data store. And I think between the threat intelligence data and our logs data, we've probably got a petabyte at least, maybe 2. And over that, we run a number of engine systems on a regular basis. Static rules, advanced models, a little bit of machine learning in there, some statistical analysis. And we test everything too. I'll get to that in a second. And out pop events that the humans do look at, and we enrich them with data. About 80% of all of the events that do manage to get to a human are already enriched with everything you'd want to know in order to determine as a human whether or not this is bad. So I guess imagine you have a binary execute on the fleet and AV triggers that it did. We obviously get the AV alert. We know that it executed. We will go grab a copy of that binary. We will run it through the binary pipeline systems, such as VirusTotal. We will know everything about the user, where the user was, how long the machine has been there, whether the machine is patched. All of this data ends up in front of the analyst so that they spend the minimal amount of time doing the toil of the uncreative work, determining whether or not the system is compromised. And because of that, these enrichment systems, these systems that do detection based on this raw data, are actually the intelligent assistants that are being built today. When we talk about machine learning, this is where we want the machines to help today. Right? We want them to be able to assist us in making determinations and pointing us in the right direction. From a team perspective, here's how we're laid out. We have a team that does threat analysis. We have a team that does security monitoring tools. These are big infrastructure projects that can store petabytes of data. And we have a security surveillance team. This is not a SOC, but it is probably what you would think of as a SOC. And we have borrowed this language from James Anderson, the idea of surveillance, not just detection. And this is the team that hunts. This is also the team that triages the events coming out of the detection pipeline. We have a digital forensics team and we have an incident management team. And we make clear lines about responsibilities so that we understand how many people we need. But in reality, a lot of the actions that we do are cross-functional. But this is probably the most important thing that we have realized, is that you should only ever have to hunt once. Our analysts, when they dive in to do hunting, think about it this way. They're doing research. They're trying to understand something new. Maybe it's sort of getting an idea of what new Windows persistence mechanisms exist on Windows 10 versus Windows 8 and Windows 7. They'll build hypotheses. They will hunt, they will iterate until the hunts work properly, and until we have cleared the backlog and we understand whether or not the fleet is compromised. And then they will write a true detector that can run all the time. And they will also write a test for it. The idea here being that you should never have signal rot. You should always know whether or not your detection works the way that you expect it to. And this cycles upon itself, but it means that we're never doing the hunting more than once, with the exception of when we have to do it against new environments. So for those of you who have companies where you acquire another company and they keep a little bit of their legacy infrastructure, redoing your hunts is actually a really good thing to do to either understand that it was pre-owned or if it's clean. Otherwise, we will use the detection in this new detection kind of development cycle, and then also as spot checks, and sometimes as training as well. We have sort of 3 kinds of hunting grounds, okay, as I call them. We have, of course, the big repository of stored raw data, which we will hunt with a SQL-like interface. We'll process it in other tools. You've heard about some of these tools. DNS logs, file monitoring, user behaviors. All of these things that sort of stand in the historical record are very good for manual hunting. But because these, in the second category, because the detection system generates so many alerts, so many things, we actually make a clear delineation between what we have high confidence in to absolutely put in front of an analyst and what we think is low confidence. And so the surveillance team will actually spend a lot of time looking in this sort of noisy mess. And here's where we really see the creativity of their specific field. People who love NetFlow will gravitate there. People who love Windows will gravitate there. And they usually have those few tricks up their sleeve that they're really good at in looking at this noisy data. And once you can find stuff in the noisy data, you can iterate on making the detectors even better. And finally, we have GER. And it was mentioned earlier in the context of memory hunting in the fleet. But we look at GER really as one of the most powerful weapons on our network. It is an agent-based system, originally designed so that we could do live forensics. We, too, had problems of needing to do forensics on machines in Brazil and not being able to get shipping so we could get the hard drive. And this has been on the fleet for 7 years. It's relatively stable, runs on Linux, Mac, and Windows. And we use it for all kinds of hunting as well. And it has a hunting interface. And I'm not going to go into the interface here, although I did last year if you want to check out that talk. But we can do almost any kind of hunting with GER in the fleet. And I'll talk about a few of them in a slide or two. So I mentioned the security surveillance team. This is effectively our attempt at making a fully automated SOC. I mentioned that almost 80% of everything that ends up in front of an analyst has been enriched with data. We also have a large proportion of incidents that are automatically resolved by the machines today. If you have something very kind of mundane and routine that we wouldn't be concerned about. And so the security surveillance team splits its time between 2 sets of activities. 40% of its time on what I like to call tactical surveillance, and this is ops. Okay, these are things that are very task-driven, things that can be completed in one shift. Event triage, hunting in this pre-processed data set, or even doing intel-driven kind of checks of the fleet to understand whether or not we're compromised by something specific. And the other 40%, they will spend looking at technology-specific projects. Google has lots of technologies. We have Windows, we have Linux, we have Mac, we have mobile. We're doing this thing called cloud. We have a very large Linux fleet. And so what we do is we actually divide the responsibilities for this 40% time amongst those different platforms. And it allows the analysts to become specialized in that field. And they will know everything there is to know about Linux persistence or everything there is to know about Mac persistence. Because we are in that situation where all of these platforms are more or less managed and treated equally. And as we know from experience, our adversaries do the same. They will focus thus on ingesting all the threat intelligence that comes out that's specific. And they will do detector development based on that data. And they will do this hypothesis-driven hunting, usually on a month to a quarterly basis, and not all the time, because it is quite intense, as we've heard from previous speakers. And they will also work significantly on automation and testing within their field. And by doing this, understanding how many platforms we have, we can understand how many people we need, and we can understand how much time they need to set aside in order to do this creative hunting and to keep us moving forward. You'll notice that this does not add up to 100%. Google has a mythical 20% that you can spend any of your time doing, and there are 3 of them in the room, and I'm not going to tell them that it doesn't exist. So, all right. I did want to talk about some of the kinds of hunting activities we might do. Some of this will overlap with things that you've heard in the last 2 days. Let's just take some examples of what we might do with our stored raw data. And again, the interface to this data is a SQL-like interface. If you've ever used Google's products, there's one called BigQuery, and it most resembles that. Typically, what we'll do is we'll build a hypothesis. And I love DNS data, so I'm going to pick on these for a little bit. Strangely enough, attackers are still using DNS hostnames for their C2, which they do so that they can easily move where it points to if their infrastructure has to be moved. The method we would use here is, of course, to compare the DNS queries that are happening on the corporate network, for which we have all of them. Every DNS query that has ever been issued on Google since September of 2009. We keep it all. And we will, in this particular hunt, what you could do is take the list that's listed here at the bottom, which is a public list, filter out those DNS host names, and figure out why anybody on your network would ever be using them. This is a kind of hunt that we might do. Similarly, and we've had pretty good success with this in the past, is to take a big chunk of data, maybe 60 days worth of DNS query logs. Sort to find the things that are first seen, as in they don't happen often. Facebook happens often, Google happens often, but something like bananatomato.kiwi.com is probably seen for the first time in this 60 days. Probably something interesting to look at. And we have actually found secondary and tertiary persistence implants using this method, which is quite interesting. Moving on to GER and how we might hunt the fleet. Here are a few things that I like to do, especially if we're going into a new environment, such as a company that we've just bought, and we'll deploy GER. And we'll just have a basic hypothesis. Maybe they've left really common artifacts behind. Lateral movement, such as @jobs. Maybe we'll find evidence of the execution of their tools by collecting all the prefetch files. These files are actually pretty small. You can collect them for a whole fleet, process them with a bash script, pretty much, understand what is executed on your fleet, and find the outliers. It's a really basic technique, and 9 times out of 10, unfortunately, I found it to be pretty straightforward. You can do a similar thing with run keys, and on the Mac, the equivalent of launch agents. And on well-maintained fleets that are small, such as just your server environment, this can actually work really well. Once you get to desktops and laptops, it's a nightmare. People have all kinds of things installed. Another nightmare scenario is we had this great hypothesis once that, and I think it was based on an Intel report, that adversaries were storing their binary blobs in registry keys, making the registry keys really big. So we thought, well, what if we just went through and found all the big registry keys that had binary data in them, download them, and figure out how bad they were? And I remember thinking, we're probably not going to find more than like 10 or 20. And it turns out that almost every camera software, for some reason, stores their binary blobs in the registry. And it was a complete disaster. So this is an example of a hunt we would choose not to automate, choose not to use again. But it was a good test to do one time, just to see whether or not we could find what we were looking for. Okay. And finally, actually I've got 2 more examples. So here's a great example of something that we did and we automated and it works really well. Any binary executed on the fleet is collected centrally. And the way that we do this is we understand deeply from our detection pipeline the things that have executed. And we will use GR to fetch a copy of the file if we have never seen it before. We will then put it through the binary pipelines. VirusTotal is a binary pipeline that we own, but we have others. And we will try to get an idea of whether or not it's good or bad. And if it's bad, we'll put it in front of an analyst to triage. Okay. And we do this for all the platforms, Linux, Mac, and Windows. And I should mention that GR is open source. If you just do a Bing search for GR, you'll find it. I actually don't know where it sits in their rankings, but presumably it's on the first page. And the team that works on this actually does a lot of public talks, and there are other teams who publicly give talks on their use of GR as well. So if you're interested in that, that is certainly available. But this has actually been a really good example of something that's easy to automate, where the results are fairly high fidelity. So the analyst is not exhausted looking at it. And finally, here's an example of a hunt that when the team proposed it, I thought was a really dumb idea, because I thought, there's no way you're ever going to pull this off. So what they did is they integrated something called ChipSec. This is an open source project that essentially enables you to get a copy of the BIOS or the UEFI, EFI, that's sort of running on the machine. And after toiling at this for quite some time, they got it to work. And interesting, all of our hypotheses were proven wrong. I had thought perhaps that a Mac fleet that's well maintained might just have one copy or one version of the firmware, because Apple is so completely meticulous about making sure that there aren't very many out there. But actually there were a lot. But they did cluster nicely into like 8 or 9 clusters. And so you could see that there clearly wasn't one outlier that looked unusual. The PC environments, an absolute disaster. Firmware on PCs, there's just no way to get uniformity, and there's actually no way to verify that what you're looking at is legitimate. Right? The people who make this hardware are not actively participating in making sure that we can verify it and that it's safe. And this is a really difficult problem. If you're interested, the team that executed this particular hunt, led by Thibault Wechstein, spoke at RuxCon last fall, and that's available up online. And all the software that they used has been open sourced, so that's available if you're interested. I think for most teams, this is not a hunt that is worth your time. But if you are a consultant and you can figure out how to do this, you could probably charge $1 billion to every org to just come in and verify their fleet for them. Right. A few other things that make me really happy hunting for. Not that I ever get to do anything real, unless I take vacation and then work during it. But last year I spoke on hunting memory and using GR and Yara. And that was mentioned earlier, so if you check last year's summit, you'll see that. And we've had good success with that. We can run Yara signatures at scale across the entire fleet. And we do that with minimal interaction to the user. In fact, the only user who's ever noticed we're doing it happens to be a Chrome developer, and he happens to be my husband. And I think he was doing it to annoy me, so It actually, the team worked really, really hard on the performance aspect of this, which was quite a challenge. We also do a fair amount of memory hunting, or can do a fair amount of memory hunting using recall, right, which allows us to get to some of the more pertinent structures, not just kind of string matching across the fleet. So my advice to you, study your history. Study your history because our ancestors actually have figured out a lot of very interesting things. And if you read the literature, especially from the 1980s coming out of SRI and the government, you're going to find some pretty interesting stuff in there, maybe some useful gems. I would also say prepare for your future. Managers, remember this kind of 4 to 5 year cycle. I am in my job now for 15 years, and I'm pretty committed to where I'm at. If you're building a SOC and you know you're going to be out in 2 years, maybe you're not going to think about this, but somebody will have to, right? So think about the talent cycle. If we're going to grow people like we grow crops, remember that you also have to help them transform at some point in their career. Think about how you do time allocation in your SOC, in your surveillance team. We like the 40-40 mythical 20 rule. Hunt once, then automate, and choose your tools very carefully and the cases that you use to use them very carefully.